What's up? I'm back. We had a slight technical hitch. My computer just decided to go, nope, I'm not doing anything anymore. Like nada, nothing, zero. I'm not even entertaining the idea of streaming live for you or any of the buttons working whatsoever. So I had to turn it all off and start again. Hello, year 13s. How are you doing? Welcome, welcome, welcome. I have, well, it looks like you guys have been having a good little chat while I've not been here. What's going on here? Ruhab, are you being helpful? Bless you. What are we talking about? Oh, transition metals. Right. Oh, colors and transition metals. Nightmare. Can I show you something? Can I show you something which I think you guys are going to lose your minds over if that's the case? Let me show you this. Even though we're on thermodynamics today, let's not forget that. But this, ladies and gentlemen, is our year 2 chemistry cheat sheet. So there's all your year 1 stuff. Here's all your equations for thermodynamics that we're using today. Rate equations in Arrhenius we talked about the other day, physical chemistry, buffers, transition metals, all the oxidation states for all the transition metals that you guys need to know about. This one obviously not considered a transition metal, but this is specific to your exam board. So in the download section of the Exambulance, you can get this cheat sheet. You can download it. Now, my advice to you is to make your own flashcards for this, okay? And test yourself on them. Test yourself on the formula. So on the front, just put iron 2. And on the back, have the formulae and the colors, okay, of all the different ones you need to know. So there'd be 3 for iron 2, 4 for iron 3. There'd be 5 here for cobalt, okay, and 5 here for copper, and obviously 3 here for aluminium, okay? So make your own flashcards on these. You just need to remember these off by heart. Learning the equations is slightly different. You're going to need to employ a different tactic for that, but learning the colors and the formulae of the different things, of the different complexes, then that is the way forward, okay? So NVR, no visible reaction, okay? That's what NVR is. So essentially, yeah, use and abuse it, guys. It's there for nothing in the Exambulance. If you, anybody here not in the Exambulance course yet, guys? Anybody not got the Exambulance course? Who's not subscribed to the Exambulance course? That's what I want to know. Okay, Miriam. So if you head to the TT website, so tailoredtutors.co.uk, you'll see a big white banner in there with the Exambulance on it. All you need to do is click biology, chemistry, or maths, and you can enroll into the Exambulance course for nothing, which is where you'll find a schedule for all our lives, some really useful materials for you to basically stay in touch with your studies. Okay, so it's basically the course which is which kind of like is the linchpin for everything that we're doing over the next few months for you guys here at Tailored Tutors. Okay, so are we buffering again, ladies and gentlemen? It does seem to be having a few issues. Mine's looking okay again at the moment. Dare I say it's looking okay? It is for you as well. Maybe it'll come back. Are we back? Are we back? Are we back? This is really annoying. Okay, I'll tell you what, let's just share my screen and we'll talk about this and see if we can get it going. In fact, are we back? I think we're back. Okay. Yeah, I just think there's so many people using Zoom right now. Families are using it just to talk to each other and what have you. And yeah, it's causing a few issues, but there we go. Right, let's just get cracking, shall we? Because what we need to do is look at some thermochemistry. Okay, so let's start with Let's start with some Born-Haber, ladies and gents. Okay, so I'm going to show you some things. So essentially, Born-Haber cycles. All right. Now, these are what I think of as basically giant Hess's law cycles. That's all they are. Okay. So hopefully I'm still okay and it's not lagging. Are we okay? You can see me moving this page around and stuff. Is that okay? Or are we frozen? What's going on? Don't like this. Okay, we're all right. We're all right. Laughing. So Born-Haber cycle, massive Hess's law cycle. That's all it is. All right. So right. I'm going to show you some definitions. I want you to tell me, please, what delta H these represents. All right. So I'm going to zoom in on these. Okay. So this first one, the enthalpy change when 1 mole of electrons is removed from 1 mole of gaseous 1+ ions under standard conditions. Now, what, pray tell, is that the definition of, ladies and gentlemen? I'm going to do this in blue. Katie says second IE, first ionization energy, ionization, second IE. Katie's got it. This is second ionization energy. Okay, so it's the enthalpy of second ionization energy. So it's the removal of 1 mole of electrons from 1 mole of gaseous 1+ ions. That's that bit there. Okay, what about this next one? The enthalpy change when 1 mole of gaseous atoms is formed from an element that's in its standard state under standard conditions. What's that one? Not enthalpy change of formation, no. It's not first ionization energy, good. It's atomization. Atomization is really, really important. So this is delta HA. So think about it. 1 mole of gaseous atoms is formed from an element in standard state under standard conditions. So for example, you could have sulfur, solid. Sorry, my pen's too big for this zoomed in. So solid sulfur, that would go to gaseous sulfur. Okay, so it's the atomization. Okay, atomization. Formation is completely different. We're going to get to that. So when you get 1 mole of gaseous atoms from an element in standard state under standard conditions. So you could have half O2 gas. Okay, that's in its standard state in standard conditions. Oxygen is O2 and it's a gas at standard conditions. That would actually form single O gas. So we've got gaseous atoms. Okay, so we've broken that up. So it's really important one, that one. Okay. Now, next up, the enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard states under standard conditions. What's that one? That's formation. Yeah, absolutely. Delta HF for formation. Okay, so we know that one off by heart. That's good. The enthalpy change of 1 mole of electrons are gained by 1 mole of gaseous atoms. What's that? The enthalpy change of 1 mole of electrons are gained by 1 mole of gaseous atoms. What are we thinking? Electron affinity? Absolutely it is. Electron affinity is specifically the first electron affinity. Okay, so first electron affinity. These are all enthalpy changes, let's not forget. So it's the first electron affinity because we're getting 1 mole of atoms and they're gaining their first electron. Enthalpy change, 1 mole of a solid ionic compound is formed from its gaseous ions. What's that one? Just while you're working that one out, example of first electron affinity, that would be O gas plus an electron gives you O minus gas. That would be an example of that. Boom, lattice enthalpy. Lattice specifically formation, good. So this will be delta H. I call it lattice, lattice, okay? Lattice association, because you're taking separate gaseous ions, boom, bringing them together to make your solid ionic substance, okay? So lattice, all right? I'm going to go through an example of that, don't worry, in a minute. The enthalpy change of 1 mole of electrons is removed from 1 mole of gaseous atoms under standard conditions. This one's first, i.e. good, so this is first ionization energy, okay? So we know all about that, that's first year stuff. Enthalpy change of 1 mole of a solid ionic substance is converted into its gaseous atoms. No, that's wrong. That should be ions. It's not hydration. None of this has got anything to do with hydration or solution or anything. Good. This is lattice dissociation. So this is lattice dissociation. Okay. Association is where the gaseous ions come together to form the solid substance. If you were to invert that, if you were to take your solid ionic substance and split them up into the individual ions, that would be lattice dissociation. Okay. Which of these two, this one up here and this one down here, is endothermic? Which one has a positive value to it? Top one or bottom one? Miss C says this bottom, endo for this, bottom this. Yeah, absolutely. So this is negative, and this is, of course, no, sorry. This one's positive, and this one's negative. Okay, so it's the bottom one. Obviously, you need to put energy in to break those electrostatic attractions, don't you? Nearly there. Last one. The enthalpy change of 1 mole of electrons are gained by 1 mole of gaseous 1- ions. What might that be? What's that describing? Yeah, good. It's the second electron affinity. Spot on. You guys are all over this. All right. Now, it's really important. I wouldn't say you need to learn the definitions per se, but they're really handy because the definitions themselves write the equations for us. So, you know, the definition of enthalpy of formation, the definition of enthalpy of combustion, the definition of enthalpy of ionization energy, they all tell us in words what the equation is. So by learning the definitions, you've got no problem in writing equations. You can always remind yourself, recite the definition in your head, and you can write an equation for it really, really easily, okay? So let's see if we can put this into practice, okay? So what we've got here is a Born-Haber cycle. I'm going to make this a little bit thinner, okay? So this is a typical question and a typical way in which you'd view a Born-Haber cycle, okay? I don't think you'd be asked to define them. Maybe it's not beyond the realms of possibility, but they don't tend to ask that many definitions. But what I'm saying, like I just mentioned, is that learning the definitions, it helps you. Reciting the definition in your head, if you have to write an equation, helps you write the equation, okay? So, what are we doing? Right. Okay. So this is a typical Born-Haber cycle, typical setup. Okay. What we normally get is our delta HF down here. That's our formation, of course, isn't it? So what would we see on the bottom line down here? What should be written on the bottom line down there, guys? Ki. Ki what? Specifically, we have got states of matter in there. Good. Solid. Ki solid. Good. Okay. So let's go through these arrows one by one. Let's do this one on the right hand side here. Specifically, what is that change? We're going from our gaseous ions. That electron shouldn't be there. We're going from our gaseous ions to the solid substance. Good. So this is delta H lattice association. Okay, don't call it formation, don't call it lattice formation, because that confuses it with the one on the other side, which is delta H formation. Okay, so try not to use lattice formation, try to use lattice. All right, so that's delta H lattice association. This is delta HF, of course, because this is what we're forming from our elements in their standard states. Okay, now when you're asked to, and it's really common to basically either write these species in with their states of matter, or at least identify these changes, it comes down to a game of spot the difference. It's literally a game of spot the difference. So if you look the difference between these two here, what are we looking at? What specifically enthalpy change are we looking at between these two? Good. So this is the delta H atomization for potassium. Good. Absolutely. Let's play spot the difference again. Which one's this one? Good. This is the delta H first ionization energy for potassium. Good. And then next one, another game of spot the difference. We're going from half I2 to I gas. Good. This is the delta H atomization for iodine. Okay. Perfect. Notice how in this one, though, we've got half I2 because we only need one, don't we, to form potassium iodide. And then over here, of course, what's left? Well, this is where the electron here is gained by the iodine. So this is the delta H electron affinity of iodine. Okay. That's all it is. Now, let's say 9 times out of 10, I'm going to do this in a different color. They want you to calculate the delta H lattice. Okay, they want you to calculate delta H lattice. Now, I'm going to show you my kind of cheat method, if you like. And it's kind of like the same method I use for Born-Haber cycles. And it's about making the arrows do the work for you. Okay, let's say that this distance up here, let me just get an arrow. Yeah, green arrow is good. This height here on the left-hand side equals the height that we got to come down on this side, right? What goes up must come down. Ras said, flip that formation. Okay, maybe that's like a tagline for me. Flip that formation. So all we need to do here is if we flip this formation and make the arrow go up for us. So let's do that. Let's get rid of that and make this arrow go up for us. All we need to do is add all these together, subtract that, okay? And what we find is this difference here. We find this delta. So if you flip that value and add them all up and then take this one away at the top here, then you get this delta, this difference here. Okay, so it's a really, really simple method. Okay, a really, really simple method in order to find your lattice association. However, it does come, it's not a perfect cheat method, because what type of value will you get? What sign on the value will you get here when you find this lattice enthalpy? Yeah, Katie, I'm just getting to that. No. Oh, lattice association is a negative value, okay? But using this method, what you're doing is you are finding a positive value. Let's say all this added to 100, okay? Oops. What happened? That happened. Let's say this added to 100. And this was 10, you're going to get plus 90 here, aren't you? So just be careful. Just be careful. When you use this method, you're going to get a positive value. Okay, you're going to get a positive value. But we know that lattice association, when they come together, energy is released. It's a negative value. So by all means, use this method. But just be careful. If they ask for delta H lattice, they're asking for the lattice association value, which is a negative value. Okay, so when you use this method, you get a positive answer. All you need to do is just flip it, just turn it into a negative answer. Okay, So what about what happens when you're in the middle, like first ionization energy? You always get the wrong answer. So in other words, the only other thing you can do, Benyon, for that is, let's get rid of all this here. You can still use the same format, okay? You can still use the same format. So all of this on the left-hand side in green equals the sum of everything on the right-hand side in going down in green, okay? Does that make sense? So what I would do is, you've been given all these values. Let's say this first ionization energy, we don't know, okay? The sum of all of these things here, including this, let's call it X, okay, equals the sum of these things here. Yeah. So all I would do is flip this arrow. Okay. Make sure you got a positive value. Flip this arrow. Make sure you've got a positive value. Okay. And then just take all of these others away and you'll end up with X. Does that make sense? So again, so if all of these on the right-hand side added to 100, and that's minus 10, minus 20, and minus 40, okay, minus 60. So that would end up being plus 30, and you've got your answer. Is that all right, Benyon? Good. You know what? I'm a fairly simple human being, and when it comes to maths and stuff like that, whatever is the path of least resistance, whatever makes sense to me, that's what I teach, and hopefully that makes sense to you guys as well. Okay, so Born-Haber cycles are nothing to be scared of. There was a question which I missed, and the answer was this. Why is electron affinity negative? Well, it's about stability. If you've got an iodine atom on its own with 7 electrons, which iodine does have, it's more than happy to accept an electron and become I-. So it becomes more stable, so energy gets released. Another way to think about it, whenever you get something positive and something negative being attracted to each other, like an electron and the nucleus of an iodine atom, energy is going to get released. Okay, and it's the same when you get positive ions and negative ions come together to form your lattice, an electrostatic attraction forms, energy gets released. So whenever you have an attraction between anything positive and anything negative in the entire world of chemistry, even when intermolecular forces come together and combine, that's an exothermic process. Whenever one thing is attracted to another, it releases energy. But then, of course, when you want to break them apart, that's where you need to put energy in. Okay, that's where you need to put energy in. So the last thing I will say, okay, in terms of Born-Haber cycles is sometimes you have to deal with 2- ions, all right? So let's say O2-. The first electron affinity is exothermic. Like I just said, energy gets released. You got an oxygen atom, only got 6 electrons and its outer energy level, an electron's coming by and it's like, oh, I'll have that, thank you very much. Energy gets released, it's exothermic, the arrow goes down. But then you need to make it O2-. You need to take an O- ion and add an electron to it. Now that is an endothermic process. We need to put energy in to do that, to go from O- and get it to accept an electron. Why is that? Okay, why is that? Katie, you're asking the same question as me. Second electron affinity is positive, but why? Ibrahim, absolutely. That's endothermic, as an already negative ion repels an electron. So you've got O-, it's already gained 1 electron, and that's fine. But you've got to add another electron to it. You've got to make it O2-. The only way you can get a negative electron joining an already negative ion to overcome the repulsion between them, you need to put energy in and say, no, get in there. You need to like force them together. Okay, so it's an endothermic process, which is why it goes up. Okay, which is why it's an endothermic process. Absolutely, it's on the content guide, Edith. 100% it's on the content guide. And I've opened up this section for you guys as well, or, you know, some of the most important videos, you know, the key videos in that section, not all of them. Okay, if you want access to everything and ask us comments and stuff like that, then you need to be a subscriber. But to be honest, you're just here to kill some time. Well, you know what? You're welcome. At least you're kind of, I don't know, educating yourself, and hopefully to a certain extent. All right, or I'm helping to educate. Now, let's talk about, what should we talk about, guys? Should we talk about delta G? Should we talk about some Gibbs? We love a bit of Gibbsy. What do we think? We'll do some questions tomorrow like we did yesterday. Oh, see, that's overwhelming yes. Okay, so let's share again. Reem's like, yeah, why not? I'm easy. I'm here. May as well do some. Okay. Yep. Oh, well, hopefully we can help you out with that, Edith. So, Gibbs free energy. Let's start with the equation. Delta G equals delta H minus T delta S. Now, oh, well, Ruhab, hopefully we can help you out here, okay? So, the point of delta G is to allow us to find out whether a reaction is going to be feasible or not, okay? So, is it feasible? That's the question, okay? So, in other words, is it spontaneous? Okay, so AKA, also known as spontaneous, AKA, will the reaction happen? And it's a yes or no. All right, that's what feasibility is. All right. All right, T-boy, hold your horses. Okay, so is it spontaneous? Is it feasible? There's lots of different ways the exam boards can put it, but essentially what it means is, will the reaction happen under these conditions? Simple as that. Okay, that's all that is. Now, the thing is, we talk about different things influencing whether a reaction is going to happen or not. We've got two major influences, well, three major influences, but I want to talk about two of them. One is enthalpy. What is more likely to occur? What is more likely to be spontaneous? An exothermic reaction or an endothermic reaction? Which is more spontaneous, exo or endo? Put that in the chat for me. Which is more likely to happen, an exo or endothermic reaction? T-Boy's saying exo, Jenny's on exo, Russell's on exo, everyone's on exo, and we have a winner. Yeah, absolutely. The way I see it, okay, here's a good analogy for you. Got a balloon, you blow up a balloon. You blow up a balloon and you just hold it, okay? That balloon, think of it not as containing air, but containing lots and lots of energy, okay? Now, when a molecule, okay, when a substance contains a lot of energy, it's not that stable, okay? Like fuels contain a lot of energy. They're not that stable. Given the opportunity to release that energy via reaction, so what happens when you let go of that the neck on that balloon, all the air naturally comes out. And that's what happens. Exothermic reactions are more likely to happen, okay? Without doing anything, it just releases all that energy, okay? So just think of molecules as a balloon full of air containing lots and lots of energy, okay? And then given the opportunity, it's like it releases all that energy, and they're happier in that ground state in lower energy formations, okay? In terms of how they rearrange themselves in terms of atoms and molecules. So exothermic reactions are more likely to happen. So in other words, negative ones, okay? Ibrahim, surprised no message went through. I asked whether or not you'll go over a drawing for Born-Haber cycle endothermic reaction. Yeah, that's true. I'm going to be doing that tomorrow. Tomorrow, I mean, this is more about just talking about rounding off the subject and stuff like that and giving an overview. Tomorrow, we're going to go through a load of past paper questions on Born-Haber cycles and Gibbs and all that sort of stuff, okay? Born-Haber cycle, BHC. So we know exothermic reactions lend themselves to feasibility. What about entropy? Entropy is the other, yeah, I'm on it, Ruhab. Entropy is the other thing. So things tend towards entropy. In other words, things tend towards being more disordered. All right, that's the natural tendency of the universe. Okay, and all matter is to tend towards entropy. All right, so what's more likely to occur? Something that has an increase in entropy or something that has a decrease in entropy? What's more likely to occur? Increase or decrease in entropy? Good, an increase in entropy. Absolutely. Okay, so let's think about this. Delta G, let's say we've got a negative delta H. Okay, a negative delta H. So we start with a negative delta H and we take away the temperature, which is always positive because it's in Kelvin, multiplied by the positive delta S. So if we take something that has something that's exothermic and something that has an increase in entropy, what can we say about the value of delta G? What's it always going to be? If we take a negative number and take away a positive number, what can we say about delta G? It's always going to be what? If you start with a negative number and take a positive number away, it's always going to be negative. Okay, it's always going to be negative. So that's why I'm making this point. Okay, that's why I'm making this point. It's always going to be negative. If you start with minus 10, okay, let's just say delta H is minus 10, and we know that we're only going to get more and more